Problem number 22. A point mass m sits on a long block, also of mass m, which rests on the floor. The coefficient of static and kinetic friction between the mass and the block is mu, and the coefficient of static and kinetic friction between the block and the floor is mu over 3. And impulse given a horizontal momentum p to the point mass. After a long time, how far has the point mass moved relative to the block? Assume the mass does not fall off the block. Solution for problem number 22. First, let's find what is initial velocity of the first block after getting impulse p. That will be v0 equal p over m. Second, let's find what is the acceleration of the point mass. That will be mass multiplied by a1 equal negative mu mg, which is force of friction, or acceleration a1 equal negative mu g. Second, let's find what is the acceleration of the block on the floor. This we can find from equation ma2 equal mu mg, which is the force of friction between point mass and the block, and minus 2/3 mu mg, which is a force of friction between block and floor. So from here we can find that a2 equal 1/3 mu g. Now we can find what is total relative acceleration of the point mass compared to the block. That will be a1 minus a2, which is negative 4 over 3 mu g. And finally we can find what is total distance which point mass cover on the block. That will be 0, which is final speed square, minus v0 square, which is initial speed over 2 relative accelerations, and that will be 3 pi square over 8 m square mu g. We can mention that till point mass move compared to the block will always move because total force is positive, which apply to the block. So it means that we can count what is the total relative distance which point mass covered on the block. That will be v square over 2a. And this is answer A. That was solution for problem number 22. Problem number 23. Assume that the drag force for a fish in water depends only on the typical length scale of the fish r, its velocity v, and the density of water ρ. A puffer fish is about 10 centimeters in length and swims at about 5 meters per second. How fast does a clownfish about 1 centimeter in length need to swim such that it experiences the same drag force as the puffer fish? Solution for problem number 23. Here we can use a dimensional analysis. We have that drag force depends only from length, speed, and density of water. So we can write proportion. That drag force proportional to this expression. Here we need to find what are our coefficients a, b, and c. Now we can use dimensions for all these variables. So we have this expression. And now we just need to equalize powers on the left and on the right for the same dimensions. So for mass we have 1 equals c. For time we have -2 equal -b. And for length we have 1 equal a plus b minus 3c. So it means that powers have these numbers. So it means that we have drag force proportional to length square, speed square, and water density power 1. The water density is the same for both fish, and if we decrease length 10 times, we have to increase speed 10 times, and the final solution is 50 meters per second, which is answer C, and that was solution for problem number 23. Problem number 24. Three boxes A, B, and C lie along a straight line on a horizontal frictionless surface as shown. Box A is initially moving to the right with the speed v, while the other two boxes are initially at rest. If all collisions are elastic and the masses of the boxes can be chosen freely, which of the following is closest to the maximum possible final speed of box C? Solution for problem number 24. We can write equation for the speed of block B after collision. For absolutely elastic collision, we have this formula, which is almost equal to 2v for mass ma much greater than mass mb. For the same reason, we can say that for mass mb much greater than mass mc, we have to multiply this speed by 2, which have maximum speed 4v. And that's answer D, and that was solution for problem number 24. Problem number 25. If a certain radioactive decay process happens n times per hour on average, then in any given hour, one expects to observe n decays with an uncertainty of square root from n. Each hour can be assumed independent of the previous one, and n can be assumed constant over time. How many hours do you need to conduct the observation so that you can determine n within an uncertainty of 1%? Solution for problem number 25. Let the number of hours we observe be h. Then the number of decays observed will be on average hn. The standard deviation in the number of decays observed in an hour is square root from n. Each hour is independent of the ones before it. When we add h independent samples of random variables, the sum has standard deviation of square root from h multiplied by sigma, with the sigma the standard deviation of the underlying distribution. So in our case, we will observe nh decays, and the standard deviation in the number of decays observed is square root from hn. So our estimate for n will be nh plus minus square root from hn. In our case, we have deviation is 1% from total number of decays, so it means that square root from hn equal 0.01 hn, and from here we can find that hn equal 10 power 4 and the h equal 10 over 4 over n. This is answer D, and that was a solution for problem number 25.